Hi everybody, in this video we will talk about the trends on the periodic table because we have a nice foundation on how electrons work after watching the first 3 videos, or maybe from your past experience. So let's take a look at how the atomic radius changes as you go around the periodic table. The atomic radius is the distance from the center of the nucleus to the edge of the electron cloud. It is usually measured in picometers, or 10 to the negative 12 meters, and it is also measured in angstroms, which is 10 to the negative 10 meters. Typically, atomic radii are typically around 1 angstrom, so that's a good way of memorizing how large atoms are. Their radii are about 10 to the negative 10 meters on average, but of course some are larger than others, as we will see. So that's a spelling error that I just noticed, so let me just cross that out. So atomic radius increases as you go down a group because the valence electrons moving down the group have a higher principal energy level and are located farther away. So in the image, focus on the gray spheres for now and ignore the red and blue areas. So focusing on the gray areas, you see that as you go down, the gray, sphere grows larger and larger. And in the image, they cut out the sphere so that you could see both the ionic radius and the atomic radius, but we're focusing on the gray area right now. So atomic radius decreases as you go right in a period, because while the valence electrons stay in the same shell, or principal energy level, there are more protons for the same shell or the same sublevel with the same principal energy level. So, because there are more protons for the same sublevel, there is a higher positive charge, which, according to Coulomb's law, makes the electrostatic forces stronger between the electrons and, the nucleus. And this causes the electrons to be pulled closer, which decreases the atomic radius as you go right. So this idea is highly related to an idea called effective nuclear charge. Effective nuclear charge is written as Z with a subscript of EFF. So effective nuclear charge is the positive charge from the nucleus felt by the valence electrons. So let me just draw the diagram for sodium. So this is sodium, and let me draw the electrons around it. So 1s2, I'll just draw it as an orbit with 2 electrons, and then it has 2s2 and 2p6. So I'll put those together in one ring, because I'll consider one ring as, one principal energy level, and it has 1, 2, 3, 4, 5, 6, 7, and 8 electrons. And then I'll draw one more ring. This is the 3rd principal energy level, and it has 1 electron. So this is, the Bohr's orbital model for sodium, and what I'll do is I'll write plus 11 for, the charge in the nucleus, since there are 11 protons, so it's plus 11 in the middle. And notice how I want to find the effective nuclear charge, or the positive charge felt by the valence electrons. So our valence electron will be the outermost electron, which will be the 3s electron. And let me tell you a little secret. Core electrons, aka the ones that are not valence electrons, cancel out the positive charge in the nucleus caused by protons. This is called electron shielding. So you can think of it this way. These 10 electrons in the n equals 1 and n equals 2 ring kind of cancel out with the positive charge in the nucleus. So there are 10 electrons, so it's going to be minus 10. And since the nucleus is plus 11, then what you're left with is a charge of plus 1. And the plus 1 charge is what is felt by the sodium. So therefore, the Zeff, or the effective nuclear charge for the sodium valence electron, will be plus 1. And this is how you calculate Zeff. Zeff is generally the number of protons minus the number of core electrons. So what I did was I did 11 protons minus 10 core electrons to get plus 1, which is our Zeff. And incidentally, the Zeff is equal to the number of valence electrons for an atom. So sodium has 1 valence electron, so it has a Zeff of 1. But this is only for an atom. So don't do it for ions or any other matter for that sort. Just do it for atoms. Now, let me tell you more secrets. Some core electrons can only partially shield the valence electrons. So what I said before about this electron canceling out with 1 proton, because 1 electron, 1 proton is minus 1 plus 1, they cancel out. Now, what I didn't tell you is that the electron can sometimes only partially shield the valence electron. So that means that not all the positive charge will be canceled out by the minus 1. Instead, maybe the electron will only cancel out a part of the positive charge. So, therefore, the Zeff can sometimes be higher than normal and be a decimal. So what this means is that the value of the number of core electrons can decrease simply because some of the core electrons are not perfect at canceling out protons, and therefore, I guess, numerically, they're worth less. And in addition, the Zeff can be higher than normal because some valence electrons have a chance to get very close to the nucleus than what is typically seen. So they feel a stronger what does that say? What? E and C? Electric, I don't know what that says. Electric nuclear charge? Oh, that's an effective nuclear charge, sorry. So they feel a stronger effective nuclear charge than usual. So remember, the effective nuclear charge is a positive charge felt by the valence electrons from the nucleus. So if an electron incidentally gets really close to the nucleus, like for example this electron here, the one that I'm circling, like accidentally goes over here, then it'll feel the nuclear charge more powerfully because it's closer, and according to Coulomb's law, the closer you are, the stronger the force you feel from the nucleus, which increases the overall Zeff. So those are 2 ways in which the Zeff can deviate from what is predicted. So let's take a look at an example. We know that sodium, by predictions, has an effective nuclear charge of plus 1 because, 11 minus 10 is 1. But when scientists actually calculate the Zeff, they find that the effective nuclear charge felt by the valence electron is actually plus 2.5. So why is this? Well, let's read the explanation I wrote. Because the 3s electron has a small probability of being close to the nucleus, it feels more positive charge there, and there's little to no electron shielding close to the nucleus where the core electrons are. In addition, the 2s and 2p core electrons may not perfectly shield the valence electrons, so the value 10, which is the value of the number of core electrons, is less than expected since they are not completely canceling out the positive charge in a nucleus like we expect. Therefore, the actual effective nuclear charge for sodium is 2.5, which means that the 3s electron feels more attraction to the nucleus than we first expected. So, nice thing to think about, but in general, by calculating Zeff, you're simply taking the atomic number, you're subtracting the number of core electrons. And remember, the core electrons are the electrons that are not valence electrons, and the valence electrons are the highest principal energy level orbitals that have S and P as their sublevels. So, for example, in sodium, the valence electron in sodium is the 3s electron. So it's either an S or P electron. And let's move forward. Let's look at ionic radius and how it works and see what the trend is. For ionic radii, let's first look at cations. Cations lose electrons, which decreases the electron repulsion. Now, electron repulsion is just when electrons are close to each other, they want to repel because electrons have the same charge, and things that have the same charge want to repel each other. So electrons that are too close to each other will want to repel one another. So decreased electron repulsion means that the electrons are not repelled as far from each other as before, which decreases their distance from the nucleus. This, in turn, decreases the ionic radius. So what is being said here is that because there are fewer electrons, if you lose electrons, then the electrons will repel each other less, and this, decreases the distance that they are repelled, which decreases the ionic radius. However, in most cases, when cations lose electrons, they lose an entire sublevel or subshell worth of electrons, and, for example, Na loses its 3s electron, leaving 2s2, 2p6 as the new valence electrons, and these are the inner sublevel electrons, and these electrons become the new valence electrons. And these new valence electrons are obviously closer to the nucleus since 2 is less than 3, so cations almost always have a smaller radius than their atomic counterpart. Now let's take a look at anions. Anions gain electrons, which increases electron repulsion. Increased electron repulsion causes electrons to spread out more, and this increases ionic radius. Therefore, anions almost always have a larger radius than their atomic counterpart. And like atoms, both cations and anions increase in ionic radius as they move down the group for the same reason atoms do. And if you want to know why, just check out the previous slide where I talked about that. So let's rank these ions in terms of ionic radius from least to greatest without using a chart. So let's try to figure out where these elements are located on a periodic table. So here's a handy-dandy periodic table. Let's circle the elements that we're looking at: lithium, beryllium, nitrogen, and manganese. So right off the bat, I can say that manganese 2+ is going to be the largest, and this is because it is located in period 4, and its valence electron has a principal energy level of 4, and all of these other ones have a principal energy level of 2. And since, 4 is much greater than 2, I can automatically assume that manganese 2+ is the largest out of all of them. So the other 3 ions that are left are lithium plus, beryllium 2+, and nitride. So let's try to order these. So notice how these 3 are in the same period. So how do we go about ordering them in terms of ionic radius? Well, if you remember, let's see. The lithium and beryllium ions lost all their valence electrons, and therefore these two actually have the same electron configuration. So these two have an electron configuration of 1s2, and it's the same as helium, and that's why these two ions are stable. Now N3- actually has its valence electron in 2s2 and 2p6. So writing out the electron configuration for these ions, I can clearly see that N3- should be larger than lithium plus and beryllium 2+. So next on the list, I can say that the second largest will be, well, N3-. Now, what about the last two? How can I tell whether lithium plus or beryllium 2+ is larger? Well, we can rely on something called the effective nuclear charge. So how does the effective nuclear charge work in this case? Well, the effective nuclear charge is just the number of protons minus the number of electrons. So for lithium, we take the number of protons. So the number of protons is, 3, because lithium has an atomic number of 3. Now, we have to subtract by the number of core electrons. Now, the core electrons are the electrons that are not valence electrons. But here's the problem. All the electrons in lithium plus are valence electrons, so there are no core electrons. So the Zeff for lithium plus is going to be 3. Now, what about beryllium 2+? Beryllium has an atomic number of 4, and we subtract it by the number of core electrons. So remember, beryllium 2+ has 2 electrons surrounding it, the 1s2 electrons, and it has only valence electrons. It has no core electrons, so this will be 0. 4 minus 0 is 4. So look at this. Beryllium 2 plus has a higher effective nuclear charge than lithium plus. So its valence electrons feel a greater pull from the nucleus than those of lithium plus. So as a result, beryllium 2 plus will be smaller, since higher attraction means that the electrons will be pulled closer to the nucleus, and this decreases the radius. So beryllium 2 plus will be the smallest, and next comes lithium plus. And we just found our answer. The order from least to greatest in terms of ionic radius will be B2 plus, Li plus, N3 minus, and then Mn2 plus. That's our answer. Let's check the chart to see if we're correct. Let's see the chart. Well, in the chart it says beryllium 2 plus is smaller than lithium plus, because we're looking at the red circles now, and we were right about that. Now, there's no N3 minus or, Mn2 plus, but I'm pretty confident that they're larger than either of the two cations that we just looked at. So, moving on to our next topic, ionization energy. The energy it takes to remove one valence electron from the gas phase of an atom or ion. So let's write out a reaction to show this. So M will be our element, and this is a gas, and we're going to remove an electron, so it's going to release an electron. So it will be M plus gas plus electron. And this is the reaction that ionization energy is describing, and it's written in kilojoules per mole of atoms, since kilojoules per mole of atoms is simply saying the energy that it takes to remove 1 mole of electrons from 1 mole of atoms, since each atom will lose 1 electron. So 1 mole of atoms will lose 1 mole of electrons, and each of them will lose 1 electron, of course. So the first ionization energy is the energy it takes to remove the last valence electron from the gas phase of an atom or ion. And the second ionization energy is the energy it takes to remove the second to last, or the second electron from the atom or ion. And it could be or it could not be a valence electron. It all depends on what type of situation we're looking at, as we'll see later. So ionization energy, well, we're talking about first ionization energy specifically, generally decreases as you go down a group, since less energy is needed to remove an electron located at higher energy levels, which are farther away and less attracted to the nucleus. First ionization energy generally increases from left to right, since the ZEFF, or the effective nuclear charge, increases from left to right as the number of protons increase in the same sublevel of valence electrons. This makes the valence electrons harder to remove, since it is more attracted to the nucleus. So as you go to the right, the effective nuclear charge increases, so it's harder to remove the electron. So that's why when you move from left to right, the first ionization energy generally increases. Let's look at the next slide. We have to do this question, and I labeled it as easy because it is going to be easy compared to the other two that I'm going to do soon. So this question is comparing sulfur and chlorine, and it's asking which one has the higher first ionization energy. So sulfur is going to be that, and chlorine is going to be that. And I'll just draw it here. Sulfur is this, and chlorine is this. So as you remember, atoms that are toward the right tend to have a higher Zeff, so therefore they have a higher attraction to the nucleus. I'm talking about the valence electron specifically having a higher attraction. And therefore, since chlorine has a higher Zeff than sulfur, then chlorine will have a higher first ionization energy, since it takes more energy to remove the first electron from chlorine. And, for that reason, chlorine wins the battle and has a higher first ionization energy. So that wasn't that bad. Let's take a look at the second question. P or C? Phosphorus or carbon? So I'll draw out where phosphorus and carbon are relative to each other. Carbon is here and phosphorus is here, and they're one group apart, and this is going to be period 2 and period 3. So which one has a higher first ionization energy? Now this question is a bit hard because phosphorus has a higher Zeff, but the electron is located farther. Meanwhile, for carbon, it has a lower Zeff, but the electron is closer. So we have contradictory, traits. So carbon, while having a lower Zeff, is closer to the nucleus. So the positive charge felt by the valence electrons in carbon is less, but it's closer, so it'll feel more of it, because closer things feel a stronger force of attraction. Meanwhile, phosphorus has a higher amount of, positive charge felt by the valence electrons, but they're farther away, so they feel it less. So how do we know which one has a higher first ionization energy? Now, what this comes down to is whether Zeff dominates or the closeness of the electron dominates, aka the magnitude of the charge Q and the radius R from the nucleus, and this is from Coulomb's law, if you remember. So which one dominates? Well, I'll tell you something special. Generally, when you're comparing periods 1, 2, and 3, the closeness of the electron triumphs over Zeff, especially when they're so close and match, since, phosphorus has a Zeff of 5 while carbon has a Zeff of 4, and if these numbers are close, then you essentially just kind of don't worry about them, and you worry more about whether the electron's closer or farther. So in this case, for periods 1 through 3, distance triumphs, and therefore the electrons that are closer will have a higher ionization energy, even though the electrons farther have a higher Zeff. So in this case, when you have competition between Zeff that's this close, then in the end, distance dominates. So carbon will have a higher first ionization energy. So carbon wins. Now what about chlorine and krypton? Now this is the same situation, chlorine and krypton. So let me draw that. Chlorine and krypton. Now krypton has a Zeff of 8 and chlorine has a Zeff of 7. Once again, the Zeffs are super close. So we don't know, which one is it for now. And notice how chlorine is closer and krypton is farther. So this is periods, I think that's period 3 and 4. So when comparing periods 3, 4, 5, and onward, the Zeff matters more than distance, since once you get far enough away, the distance doesn't really matter when it comes to attractions and, the ionization energy. So in this case, the Zeff actually dominates, and the element with the higher Zeff will feel a stronger pull, and thus will have a higher first ionization energy. So krypton wins, and in this case, krypton has a higher first ionization energy. So these questions are considered hard, so don't worry if you don't really get them because they're pretty hard, but if you do get them, good for you. Let's compare two more elements, N or O. Okay, so N is here and O is here. And you might be expecting, oh, this is obvious, O has a higher ionization energy since it has a higher effective nuclear charge. Now, this is wrong because if I write out the electron configuration for nitrogen, this will be the 2p, and oxygen will be here. And if you notice, nitrogen looks like that, and oxygen looks like this. And here's a tip of advice. Removing an electron from a pair is easier than removing something that's half-filled. Remember, being half-filled or fully filled, like, in the d orbital that I talked about in the previous video, those things tend to be stable, so this half-filled subshell is pretty stable. So removing an electron here is actually harder than removing an electron from here, even though oxygen has a higher Zeff. So that's why nitrogen in this case has a higher first ionization energy, and this is yet another exception, and it's hard, but, you'll learn. Alright, let's talk about the second ionization energy, sodium versus magnesium. So for this question, I had to write the electron configuration for the +1 form of these elements, and that's because the second ionization energy is the energy it takes to take away an electron a second time. So the first time is the first ionization energy, so I just skipped that because we're not worrying about that. We're worrying about the second ionization energy. The energy it takes to remove the second valence electron, or the second, final electron, or whatever you want to call it. So let's figure out which one takes more energy. Is it easier to take an electron from the 2p sublevel or the 3s sublevel? Well, Mg wants to be Mg2+, because it wants a full octet. It wants this 2s2, 2p6, and by losing this, it can become that. So Mg2+ is 1s2, 2s2, 2p6, and Mg2 is happy. So removing this electron will take very low energy. Now what about for the sodium plus? Well, if sodium plus becomes sodium 2+ by removing a second electron, it's 1s2, 2s2, 2p5. And what you're doing here is that it's already stable, and you're making it less stable by, removing an electron. Why would the sodium want to do that? It will resist against you, and because of that, it will take a lot of energy to remove this electron, so it'll have a high ionization energy for that electron. So sodium wins this fight, and sodium has the higher second ionization energy. So let's move on to the next topic, electronegativity. How badly an atom wants to attract itself to a shared pair of electrons or a covalent bond. And electronegativity is unitless and measured relative to other elements, so there's no units for electronegativity. Now, electronegativity increases across a period because Zeff increases across a period. In other words, there will be more protons for the same valence electron sublevel, and the atom will be more attracted to the electron pair in the covalent bond. So for example, if we take two elements like N and C, according to this table, N has a higher electronegativity than carbon, since N has a higher Zeff, which means that the protons pull on the electrons more strongly. And remember, electronegativity is just how badly an atom wants to pull other electrons toward itself. So since N has a higher Zeff, it pulls electrons closer, so it wants to pull them more badly. So N will have a higher electronegativity. So if you have a bond between N and C, then N will want to pull these electrons, this electron pair in the covalent bond, toward itself more so than carbon does. And we'll talk about this in future videos when we talk about covalent bonds. Now, electronegativity decreases down here because the pair of electrons in the covalent bond are located farther from the nucleus, and according to Coulomb's law, they will be less attracted to the atom since they are farther from the nucleus. So I don't think that's as hard to understand. So if you don't understand it, just read it over and think about it. All right, moving on. Electron affinity, change in energy when an electron is added to an atom. It is measured in kilojoules per mole. It's kind of the same thing as ionization energy, but in this case, it's the energy it takes, or it's the change in energy when you add a mole of electrons to a mole of atoms in the gas phase. And electron affinity and electronegativity all relate to the fact that an electron wants to go with an atom. And since they are very similar concepts, albeit a little bit different, they generally have the same trend, but it is less obvious for electron affinity, and it's much more complicated. And I'm not going to show you the trend for electron affinity on a table in terms of numbers because it's pretty complex. And just think of it as the same trend as electronegativity, and you'll be perfectly okay. Now, two more terms. Diamagnetism, when electrons are weakly repelled by a magnet because they have no unpaired electrons. So for example, calcium is diamagnetic since its valence electrons are, in a pair, and there are no unpaired electrons here. Now, meanwhile, paramagnetism is when electrons are weakly attracted by a magnet because they have unpaired electrons. So sodium has an unpaired electron there, and that's why sodium and its electrons will be weakly attracted to a magnet, while calcium will be weakly repelled by a magnet since its electrons are weakly repelled by a magnet. And that's all for this video. And I'm happy I kept it under 30 minutes since that's always my goal. And have a nice day.